This video is for examples 13.6, 1, 2, and 3, which are all in relation to theorem 13.6.1 in Greenberg's book. So the point of theorem 13.6.1 is if we have a constraint relation between two variables, f is the constraint function of x and y, such that f is equal to 0, and in examples 13.6.1 and 13.6.2, the constraint function is x squared minus 4 y squared minus 4. Okay, again, this is called a constraint function. It depends on two variables. And the question is whether or not we can define a function. And I'm going to depart from the book's notation and be a little bit rigorous, a little more rigorous than the book. So I'll put a little tilde over the y, meaning that now we're going to be treating y as a function of x. And just to remind ourselves that we're treating y as a function of x, and not as an independent variable, I mark it with a tilde. Okay, and so the question is, can we define using that constraint relation? Does there exist some function y tilde, and is that function y tilde unique, starting from some particular value of x? Okay, and so example 13.6.1 is basically phrased in terms of conic sections. We know, because we're old and wise, that the solutions, the real solutions, x and y, to that relationship form an ellipse in the plane with a 2:1 aspect ratio if this is x and that's y. Okay, so now the question is, starting at some particular value of x and y that does satisfy that relationship, can we construct the implicit function y tilde starting at that point x? Okay, and so the theorem (13.6.1) basically says that if the partial of f with respect to y is not equal to 0, then we're guaranteed, well, and there, let me write it more formally, then there exists a y tilde of x in at least some neighborhood of x naught, such that if I evaluate the constraint function, it's satisfied. So f, if I evaluate it at x and y tilde of x, then we have the constraint realized. Okay, so now let's think about a couple different values of x and y that satisfy the constraint relation and see if we can define a y tilde starting from that particular x value. Okay, so in example 13.6.2, we're asked to consider the point x naught equals 1, and then we can determine that there is a y value that satisfies the constraint relation at x equals 1, and that y value is, well, it could be plus or minus, but let's say minus square root of 3/2. So clearly, if I choose that value of x and y, I satisfy my constraint relationship. But then the question is whether or not I'm guaranteed, so does there exist, question mark, y tilde of x starting at x naught equals 1. So can I define that inverse function? And so what do I need to do? Well, I ask the theorem, so is the y partial derivative at f of f evaluated at that point, it's not equal to 0, that means bingo, the theorem tells us that there exists a y tilde at least in some neighborhood. Okay, so we start at x equal 1, and of course we cannot increase just looking at the ellipse, we can't increase x past 2, and we can't decrease x past -2, otherwise our function y tilde will cease to exist. But the theorem guarantees that at least in some neighborhood, we're good, and we are. But now, let's check on the point if x is equal to 2. Y is equal to 0. So this point certainly satisfies f equals 0. So that pair of points satisfies the constraint relation, the pair of coordinates. But now if we check fy is equal to 0, so that tells us that the theorem doesn't say anything. Okay, so we have to appeal to being clever or doing something outside of the parameters of the theorem, which gives us something automatic. And in this case, we look at the ellipse and we can convince ourselves that there does not exist any y tilde of x, because if I increase x by an arbitrarily small amount past 2, then there's no y value that satisfies the relationship. And finally, I want to briefly discuss example 13.6.3. 13.6.3 is a little more realistic in that we have a constraint relation that isn't immediately familiar to us. So I don't know about you, but I could not draw the curve in the plane. I don't know if there's one curve. I don't know if there's many curves. I don't know how many solutions, how many different curves, what the set of all solutions to this relationship looks like. It could be complicated in the plane. Okay, it could be complicated, but we know that x equals 1, y equals 2. We can plug in the values of x equals 1 and y equals 2, and that tells us that this constraint relation is satisfied at 1, 2. So let's start at that point, and let's ask whether or not we can construct. So can we build a, can I consider x as a function of y starting at y equals 2, or can I construct y as a function of x starting at x equals 1? Can I do either one of those? Okay, so if I look at if I look at the partial derivatives of the constraint function, I take the x derivative, so this is my constraint function f. If I take the x partial of my constraint function, that gives me minus 2 e to the y minus 2x. And if I look at the y partial is y minus 2x plus 1 times e to the y. And if I evaluate fx evaluated at 1, 2, so x is equal to 1, y is equal to 2, minus 2 e to the 2 minus 2. So that's not equal to 0. Then if I look at fy, the y partial, evaluated x equals 1, y equals 2, that's going to be 2 minus 2 plus 1 e to the 2, also known as e to the 2. That's not equal to 0. So what the theorem tells us is that I can either consider x to be a function of y or y to be a function of x starting at 1, 2, and I can build a perfectly legitimate function, either x tilde of y or y tilde of x. Okay, so since this is a complicated constraint relationship here, we don't have a name for x tilde as a function of y or y tilde as a function of x. So for our example of pushing a mattress or a piano up a hill, we had a name for the inverse function. The function itself was cosine, and its inverse we have a name, arc cosine, since we use it so often. So these functions here are anonymous. But we could construct them, for instance, numerically if we wish. We also do not know how far, in terms of changing y, this function will remain well-defined, and we do not know how far, in terms of changing x, this function y tilde will remain defined, but we know that there's at least some neighborhood about x equals 1 where y tilde will be defined and unique, and we know that there's some neighborhood around y equals 2 where x tilde will be defined and unique. So this is how we apply the theorem 1361 to decide whether or not a constraint relation between two variables will be able to generate a function of one in terms of the other.